All right, thank you. You've probably heard of the Polar Vortex. It's responsible for extreme cold weather in our area, and this is associated with waves along the upper level jet stream. There's a theory that says that under global warming, Arctic ice will melt to some extent and the amplitude of this wave will increase, thereby increasing the probability of these extreme cold outbreaks. There have been many papers discussing this. We approach this in a very different way, which I'm going to discuss. The temperatures in this area are pretty well characterized by a Gaussian distribution or bell-shaped distribution. It's characterized by two parameters, a mean and a standard deviation. Now, if you have a theory that says that under global warming, the probability of these cold extremes will increase, that means the probability has to go up on the cold side. And if you have a wave, you have an equal and opposite. So as the wave moves around, you would also have a higher probability of the warm events. And so when you put those two together, that would imply the spread of the PDF has to increase, or the standard deviation has to increase. And so if you have more jet stream waviness, we would expect to see more variance, and that's a testable hypothesis. So that's what we looked at. This is showing, the black curve is showing the standard deviation of daily temperature from 1950 to 2015. Let me emphasize the black curve is not showing a time series of temperature, it's showing the standard deviation of the temperature within each year. But you can see over the past 50 years, very little change in terms of the overall trend in that black curve. However, comparing variances is not so easy if the variables are persistent or autocorrelated. And so there's a standard procedure that in order to remove that persistence, this is called a whitening transformation. And that's what is shown in the red curve below it. So this is showing the standard deviation after you remove the persistence effect of temperature. And what you do see is the standard deviation is decreasing over the past 50 years, not increasing. So it's the exact opposite of what this theory had proposed. So if you put that information together, we think the distribution of temperature looks like this. In 1950, it looks like the blue curve, and today it looks like the red curve. And you'll notice that the variance of the red curve has gone down, and that the probability of the cold extremes has actually gone down, not up, in contrary to the hypothesis, and that the probability of warm events has actually gone down. Now, why is that changing? Most of our extreme cold temperatures come from temperature advection. What that means is you're familiar with the fact that temperature tends to decrease as you go toward the poles. And so when you have air blowing from the north, that's bringing cold air toward us, and that's responsible for extreme cold air. Conversely, if you have air coming from the south, it's bringing warm temperatures toward us, and that gives us our extreme warm temperatures. But at the same time, there's global warming. This is a map showing the temperature change over the past 100 years, and you can see that the temperature change is maximum toward the poles. That's called Arctic amplification. And if you look in our area, to the south of our area, there has been relatively little warming. That's called the warming hole. And to the north of us, there's been quite a lot of warming. And so when you put those two together, what's happening is the temperatures to the north of us are actually decreased. And so the amount of cold air that we're getting from there is decreased, and that decreases the variance. And so when you put Arctic amplification and advection together, we predict that there's a variance decrease. So the answer to the question, are winters becoming more extreme? The answer is no, winters are actually becoming less extreme, at least along the US coast.